The compression member shown in figure 5.3a consists of a solid aluminum bar, which has an outside diameter of 100 millimeters, a brass tube B, which has an outside diameter of 150 millimeters, and an inside diameter of 100 millimeters, a steel pipe C, which has an outside diameter of 200 millimeters and an inside diameter of 125 millimeters. Given the elasticity of the aluminum, brass, and steel are 73, 100, and 210 gigapascals respectively, please determine the overall shortening of the member under the action of the indicated loads. All right, here is, get rid of my picture, there is the system. Aluminum bar A, so that's this top one, that is solid 100 millimeters, so that has a certain area. And then I have B, which, okay, and I had a load on that, and then I add more load at that plate, and then I have this middle section, which is brass, and then a lower section, which is steel. The geometry, the ID, the OD are given. These are hollow, and those plates transmit the loads, okay? And you can see my loads keep going up, all right? Determine the overall shortening of the member under the action of the indicated loads. So, hold on, cough. So, we just have to start punching away on this. Remember, the equation that we've got, delta is equal to PL over EA, and that's going to apply to each section. And then we did have also the total deflection for wedding cakes. I built that right into the equation sheet. The total deflection is the sum of the individual deflections, which is PL over EA for each section. So let's start going through it. And I'm going to be a pain in the neck about it. I'm going to do things probably the slowest way possible, but I hope it's going to be the most thorough way possible, really, as well. And that is the total deflection is equal to the deflection of the aluminum plus the deflection of the brass plus the deflection of the steel. The deflection of the aluminum is equal to the load in the aluminum times the length of the aluminum times the area of the aluminum times Young's modulus for the aluminum plus, and this is where you should be hitting the play this back at 200% speed, the load in the brass, the length of the brass, the area of the brass, the Young's modulus for the brass, maybe go to 400%. The load in the steel. Oh, my screen's jumping around now. The load in the steel, the length of the steel, the area of the steel, and the Young's modulus for the steel. And now we just start filling in values. The load in the aluminum is, well, and the way to do that really is to say, look, if I draw this, and let's draw, I'm drawing this over on the side here. And I'm just going to draw the first two sections and then hide that. If I were going to cut this, here, the only load I have on this right now is 650 kilonewtons. And so if I were going to cut that, then what I get is I'm going to get this squiggle, cut this with my load of 650. I know the system is in static equilibrium. So this force back, that has to be 650. And so by cutting it there, I can see what that is. And then if I would cut it again, if I cut it there, well, I don't remember what that second load is, 850. So this is 850. So then this reaction force here is going to be the 650 plus the 850, so 1500. So you can see how I'm building up these pieces. But let's go back to my equation. The load in the aluminum is 650 kilonewtons times the length. Oh man, I'm going to go back and forth to this thing over and over. 1 meter divided by the area. Okay, I actually got to go to the problem statement. Outside diameter of 100 millimeters or 0.1 meters. So now my area is pi. That was my diameter, so it's 0.1 squared over 4. That's my area. And my Young's modulus, it gave that to me in the problem statement, was aluminum is 73. Aluminum is 73. So 73, and that was megapascals. I think. Gigapascals. There you go. I got a e to the 3 problem here. So let's get rid of the whole thing and rewrite that. Gigapascals plus, and now we got to do it for brass. The load when in the brass was 1,500 kilonewtons times the length is 1.25 meters. 1.25 meters, that's L, divided by A. Problem statement says a 150 OD and a 100 ID. So pi over 4 times 0.15 squared minus 0.1 squared times Young's modulus for this, the modulus of elasticity for the aluminum, brass, and steel. Brass is 100, all right? 100 GPA. And then I got one more term to do. Let's let's just erase this because I haven't been keeping this stuff anyway, so. Plus the load in the steel. Let's take a look at the figure again. I got to actually slide it out here. Plus another 1,500, so that's going to be plus 3,000 kilonewtons. Somehow my 3 moved. Something 3,000 kilonewtons times my length, which is 0.75 meters, times the area. I got to go back to the problem statement. This has an outside diameter of 200 and an inside diameter of 125. So this is pi over 4, 0.2 squared minus 0.125 squared. And then the Young's modulus for that was 210 GPA, 210 GPA. And that's going to be my answer. Let's get rid of the problem statement. I just have to run the calculation. So let me grab my trusty dusty calculator. Boom, and there we are. So I calculate this out, and you get, oh, there you go. That's these are all units of meters. Should have put that in. 001, and I was consistent in terms of having those units up above. Do my units all work out? So this would have been in areas of units of meters squared. So this is kilonewtons. So that's E3, well, Newton, and then times meter divided by meter. So it's kilonewton per meter, gigapascals. I guess we have to. I want to run my units a little more carefully before I just go. Yeah, this is all good. A newton, a meter squared, and a pascal are my units. A pascal is equal to a newton per meter squared. So I drew it in red, so I'll cross it out in blue. My meters squared cancel, my newtons cancel, and so I'm left with meters. So I'm good on the units. and then I got my answers for each, and then here's my total deflection. Now, if you're paying attention and playing along in the book, what you're going to see is that they have a deflection as negative, and maybe I should look back at the problem statement, which would be here. Determine the overall shortening. Well, it's 3.6. What they did is they ran the they looked at the force when they had their figure on their wedding cake, and they said, "Hey, that's in the negative direction." They threw a or negative y, maybe pick your coordinate system. Y. So that force was negative, so that caused the answer to be negative because the force was down. Can't see the picture with So that force is down, but that we know the sign convention that we used. I was looking at the deflection in each, and because that force was down, we knew the direction to be. You could, I guess, argue that I did not draw a coordinate system that way. I drew a coordinate system that way, and that gives you my deflection. And maybe I got a little sloppy because I knew what the answer was going to be, and everything was pointing in the same direction. Everything was working to make the section shrink. So I was not careful in following through. Another thing I want to point out is the use of significant figures. You would say, well, if I'm only going to grab 3 significant figures, maybe I should have stopped there. Well, no, that's not 3 significant figures technically. This would be 3 significant figures. But when you start adding them to the next deflection, these 3 significant figures don't even show up. That's a 0.5 millimeter, where this is running almost 2 millimeters. So this is almost negligible, even if you track the 3 figures. So you kind of got to pay attention to those aspects of problems. You can run extra digits and then start collapsing things at the end once they add together, once you figure out. I mean, this is the biggest part of the answer. That's almost 2/3 of the answer right there. 2/3 of the deflection occurs in the brass. So, and then I guess one more thing to think about. 3.6 millimeters, that is going to be about 0.140 inches in the neighborhood, something around there. 3 millimeters would give you 120 thousandths, and then another 0.6 will give you another 24. So 145,000. Fine. 145, eighth of an inch. Think about it as an eighth of an inch. But look at how big this thing is. Look at how big this is. This structure. Sorry, I got to get over here and grab it. This structure is 3 meters tall. It is about 10 feet tall, and you put 650 kilonewtons on it, and it goes down an eighth of an inch. Wow, that stuff is stiff. Now, I got another question. I got to look something else up. Hold on, because how big is 650 kilonewtons? All right, so here's your fun fact for the day. This 650 kilonewtons here is equal to 145. I just got to write out the zeros. Pounds. Okay? When they take this 10-foot tall object, they're putting 35 minivans. 35 minivans on the top. And then, right? Do you remember they put more there? There's another 850 there. So here's another probably another 50 minivans. And then here's 70 more minivans. That's how they load that thing. That's how they load that thing. Oh no, sorry, not 70. Not 70. This is going to be 85 minivans at that level. So this thing's supporting a total of just crazy. Crazy. Let me do one more here. Yeah. 674,000 pounds. That's 674,000 pounds. I don't know, is that like two 747s? Do you remember how big that is? This is only like 8 inches across, right? I think it's only, let's get our problem statement again. Problem statement there. The outside diameter is 200 millimeters. So yeah, that's about 8 inches across. Crazy. Crazy. The materials that we're working with are just absolutely amazing. And I need you to put some of these things in context, because we have to have a physical sense of what we're doing. When you're talking about designing buildings or designing cars or designing, you have to know how strong are the things that we're going to work with. And so I'd like you to develop a physical sense of that. Now, I've worked my whole career in inches and in pounds, so I have to go back to that to get kind of a baseline to compare. And honestly, I don't know. I don't have a sense for what 674,000 pounds is, but I can start to compare that to, it's about 120 minivans. Well, they're 4,000 pounds for a minivan, so no, it's going to be 150. 600,000 pounds will be 150 minivans, and then I got another 74. Well, and what did I add? 150, and I'm saying it's 85 plus 85. There's 170 minivans. Man, it's okay. That's an amazing, amazing amount of force to be dealing with. So, and oftentimes when I'm working a problem, if it's in metric, I have to convert it to English in order to understand it, because that's what I'm used to working. I don't care if you want to have a sense of what the newtons are, or if you want to have a sense of what the pounds are, but when you get answers, start thinking about them in terms of things you know, whether that's minivans, whether that's elephants, whether that's I don't know. I don't know. Whatever helps you understand the physical size. Don't just deal in a meter. I know what a meter is. It's just over 3 feet. I'm just under 2 meters tall. But have a sense of what those dimensions are that you're talking about. You're just throwing around willy-nilly. All right. Hope you're well. Talk to you soon.